Okay, hello guys. Okay, so this video is about the application of GS. First of all, please remember to bring your pens and notebooks. Okay, and prepare for the lesson. Okay, first we need to do a bit of revision about the idea of geometric sequences. Okay, so for a geometric sequence, Okay, geometric sequence is a sequence of a common ratio. Okay, so the recursive rule is Tn plus 1. That means m plus 1 term equals its previous term times r. Yeah, and we also have an explicit rule. Okay, so in the textbook or in your formula sheet in the examination, they use this rule. Nth term equals first term times r to the power n minus 1, right? But we also talk about a generalized rule. Okay, so this one is worth remembering because it's quite useful. Remember as n greater than n. Okay, so for the generalized rule, we can start for any term. Okay, and just remember you need to adjust the power of the common ratio. Okay, good. Okay, so remember that for any geometric sequence, the key is there must be a common ratio. Okay, no matter what form you are using. Okay, so today we're going to talk about some applications about geometric sequence. Okay, so first we are talking about an idea of exponential decay. Okay, what do we mean by exponential decay? Okay, an exponential growth. So an exponential growth is a growth of quantity which increases at a constant rate. Okay, so what do we mean by constant rates? That normally the rate is something related to time. So for a constant rate, normally it means a quantity increased by R% each year. Okay, if some quantity is increased by R% each year, of course sometimes it could be days, it could be months, but normally in the context of a textbook, it's about increase by R% each year because it's increasing, so that means it's a growth. And the growth rates and the growth percentage are different. Okay, so R% here, this is what we normally call a growth percentage. Okay, but growth rate is different. Okay, growth rate is 1 plus R%, 1 plus the growth percentage. Okay, for example, if something is increased by 10% each year, okay, then its growth rate would be 1 plus 10%, and it becomes 1.1. Okay, right? So how can an exponential growth be represented by a GS? All right, so let's have an example. Example, say a city of population like 1,000 now. City of population 1,000. See a growth 10%. 10%, 10% each year. Okay. Okay, so that's an exponential growth because you see that's a growth of 10% each year. Okay. Right. So again, that 10% growth percentage. Okay. And population 1,000 here is what we call the initial amount of the quantity. Okay. That's what we call initial quantity, initial amount. Okay, and that's the growth percentage. Okay, so let's see what happens of the population at the end of each year, right? Okay, so let's say is at the end of, okay, and the population right. So let's write something here at the end of first year, second year, third year, okay, and nth years. Okay, so let's see what happened to our population first at the end of first year. So at the beginning of the first year, that's 1,000, right? So it increased by 10%. So at the end of the first year, it should be 1,000 plus the increase of the population. It will be 1,000 times 10%, because that's 10% of the population at the beginning of the first year. Okay, so if you do the calculation, of course you can use a calculator, but you can also observe that if we take out common factor 1,000, it becomes 1 plus 10%. Okay, so I try to do this to show you that's growth factor. Okay, so that means 1,000 times 1.1. Okay, it will give 1,100, isn't it? Okay, so that would be a population at the end of the first year. So how about at the end of the second year? Okay, so if there's another year, okay, so how could we calculate the population? Remember that at the end of the second year, you need to use the population at the end of the first year, okay, to calculate the population at the end of the year, right? Okay, so you need to use 1,100 as the population at the start of second year, right? Right. So use the same formula, except that we are now using 1,100. Okay, so pretty much would be the same technique, but this time we use this one. Okay, so that would be 1,100 times 1.1, right? Okay, so that will give you, okay, 1,210. So how about third year? Okay, so you see each time actually we multiply 1.1. Okay, at the third year you are going to multiply, that's 1.1, but use the numbers at the end of the second year, right? Okay, so that becomes this number. And how about nth year? Okay, so n is any number, so we need to find a general formula. Okay, so let's see if we could establish something like a GS. Okay, because we are going to see how exponential growth can be represented by a GS. All right. Okay, let's define Tn would be the population at the end the nth year. Okay, right? And so what happens is, if we have a look at the previous 3 years, you could see from first year to second year, you multiply by 1.1, right? So do you see a pattern of GS? Okay, so basically that means you will have, okay, so basically you see that's a GS, but what's the term you start with is, do you start from the first T1? No, because T1 here is the population after the at the end of the first year. Okay, so actually we're going to start with T0. Okay, so T0 is what we call the starting. May I use the initial population? Okay. Okay, if we use T0, so what's the GS for us? It should be Tn equals T0 to R. So what's R? R would be the growth factor, right? So R would be this number. Okay, this number, right? Okay, to power what's n, not n minus 1, because you start from 0. Okay, right? Okay, so that would be a formula. Okay, so if we use that formula for here, then what's the general expression for the population at the end of the nth year? It should be something like Tn equals, what's that T0? It should be 1000, right? Times R will be 1.1, and to the power n. Okay, so that's what we call an exponential growth of population. Okay, so yeah, exponential growth, you need to find the growth factor. Okay, so that's ours, what we call the growth factor. Okay, so the growth factor is 1 plus the growth percentage. Also, you need to have an initial amount of quantity, which is T naught or T0. Okay, and T naught would be the initial amount of the quantity you are given. For example, in this case, would be the initial population. All right. Okay, so that's basically the idea of exponential growth. Let's do one example. Right. So in this example, okay. So sorry, there's an experiment here. Okay. Okay, so in this example, the area of a forest is increased by 10% each year if the initial area of forest 400 hectares. Calculate the area after 5 years. Okay, so in this question, sorry, I need to change the color actually. Okay, A, let's see what's our initial quantity. Okay, so our initial quantity should be T0 through 400. Okay, and also you are now going to find T5, and T5 equal T0, and you need R to power 5. But what's our growth factor? R is R 10%? No, R is 1 plus the growth percentage. So growth percentage is 10% in this case. Okay, so it's 1.1. All right. Okay, so now we got the formula. You have 400 times 1.1 to power 5. Okay, so that's the number of hectares we have. All right. Okay, so okay, we need a bit space for our part B, so let's move that to here. Okay. Okay, how about part B? Determine the least number of years it requires for the area to be double. All right. Okay, so in this case, you need to find the number of years. Right, so the formula is still be this one, Tn equals T0 r to power n. So how about Tn this time? We don't know which year, but we know that Tn should be the double of T0. Okay, so 2 times 400. So this is 400 times r to power. So r is 1.1 to power n. Okay, so that will give you 2 equals 1.1 to power n. Okay, how could we solve this? So you need to find n, which will make 1.1 to power n greater than 2, but just greater than 2. Okay, so you need to find the least number of n such that 1.1 to power n will be greater than 2, right? Okay, how could we do this? Of course, you can use a calculator to substitute numbers, integers into n until it just bigger than 2. But that's another way to do it. If you remember, let's use the calculator, right? Okay, in your calculator, you can, sorry, just get it wrong. Okay, you go to menu and you can go to action. You define a function, okay, which equals 1.1. Remember that's our right hand side. It's 1.1 to the power of n, right? So the power, okay, so the power is x. Oh, okay, right, so then you see done. That means it's well defined now. Okay, then you can just input numbers. For example, I'm going to try, how about 6? So 1.1 to power 6, so it's 1.77156. Okay, remember that you are looking for a number such that it will come close to 2. It should be just bigger than 2, right? For the area to be double, so you need some n which make it just bigger than 2. All right. Okay, so 6 is not the answer. Let's try 7. Okay, so you come close. Okay, but our target is still 2, so you still need to move on. Okay, now when you put 8 into x, you see that it's bigger than 2 now. So that means x should be 8 if you want to have 1.1 to the power x greater than 2. All right. Okay. So I go back here. So by our calculator, we know that's okay. The least number should be 8. Okay, so it takes at least. That means it takes at least 8 years for the area to be doubled. Okay. Okay, so that will be the second part of our question. Okay. And the reason we need to learn that exponential growth is for us to understand the compound interest investment. Okay, we know that we have learned something called simple interest investments. If you still remember, for simple interest investment, okay, let's have a bit of revision here. For simple interest investment, simple interest investment. Okay, what happens if you still remember that? Okay, we use it's like arithmetic sequence. It's like a AS, right? So we say that okay, amount at the end of nth year will be equals what? Initial principal. So that's the principal plus, okay, plus m times, okay, the simple interest. Okay, if you still remember that, the simple interest would be just like p times r%. Okay, so that's the interest rate. Okay, so that's the simple interest. Because for simple interest, why this is an AS, you can think, you can look at the thing like this: Tn equal to T lot plus n times D. Okay, so that's Tn means the amount at the end of nth year. T0 means the principal, and D just means the interest. So that's why it's an interest. It's an AS. Okay. Okay. For simple interest, the main feature is that the its principal will be always fixed at the beginning of each year. Okay, and so the interest will be fixed for each year, right? But for compound interest, it's quite different, okay? Because a compound interest investment grows at a rate of 1 plus R%, okay? So that's R%, it means the interest rate. Okay, so let me give you one example. Okay, for example, now, if we have a principal, let's say it's an initial investment, which what we call the initial, or what we call principal, which is okay, $1,000 again. Okay, the interest rate is what we call 6%. PA. P means per annum, means yearly interest rate. Okay, compound yearly. Okay, you don't need to be worried too much about that compound yearly. That just means we calculate the interest on a yearly basis. Okay, so you calculate the interest every year. That's it. So for all our questions in the book, all interest will be compound yearly. There's no exception. Alright, so that's interest rates. And how about, okay, so let's see. Okay, and okay, let's say this one is our first year. Okay, okay, our first year, second year, and third year. Okay, okay, let's say this one is what we call the principal. At the start of first year. Okay, so the end of. Okay, so there are two numbers. One is the principal at the start of each year, and the other number is amount at the end of each year, right? Okay, so at the start of first year, of course, the principal would be the initial investment, which is $1,000. Okay, which is $1,000. Okay, so how could we calculate the amount at the end of first year? You will use that $1,000, okay, plus $1,000 times the interest rate per year, which is 6%. Okay, or you might just write like 1,000 times 1 plus 6%. Okay, and that number will goes to is 1060. All right, so that's the amount of at the end of first year. So how about at the start of the second year? Okay, if that's simple interest, remember that for the simple interest, the principal at the start of each year will be always the same number, will be always equals the initial amount. But for the compound interest, okay, the principal at the start of the second year would be the accumulated amount at the end of the first year. Okay, so that's why at the start of second year, okay, the principal now becomes okay $1,060. Okay, so that means the principal itself is growing. Okay, just like a compound, it's just like an exponential growth. That's why we say compound interest is an exponential growth. Okay, in terms of the amounts will accumulate for the percentage increase each year. All right, okay, so for the second year you are not going to use $1,000 as your principal, you are going to use 1,060. Okay, so how could you calculate the amount at the end of the second year? You use that 10 times 1 plus 6% again. Okay, so that will give you okay, so that's the amount. And the third year, again, you need to update the amount of the new principal becomes this one, and the amount at the end of that year would be this one. Okay, so do you see any resemblance between exponential growth here, okay, and the compound interest here? Actually, they are the same essentially, right? Okay, so actually that growth rate is now 1 plus interest rate. That's it. Okay, all things are the same, and the initial amounts in the in an exponential growth. Now in the compound interest investment, it's just the principal, what we call the initial principal or initial investment. Okay, right? So that's why we can change that into represent that in our GS again. Okay, remember that in this case we can conclude, because each time you actually multiply, that's 1.06, multiply that's 1.06. Okay, so that means a growth rate, growth rate factor Oh, sorry, just growth factor would be good. Okay, sorry. So the growth factor would be 1.06. Okay, so that's our R. Okay, and also your formula would be like this. Again, we're going to use this one. Okay, just like an exponential growth, but this time that's Tn would just be our An, right? That T0 would be our principal, and that's R would be our 1 plus R% interest rate to power n. Okay, and remember, when you have this thing, the An, that means amount at the end of nth year. Okay, if you don't want to use the new symbols, you might just like what we did in arithmetic sequence. I mean the application arithmetic sequence, you can still use Tn if you like. All right, that's totally fine with me. Okay, I do that because in your textbook they use the symbol An and P, things like this. So I just need to give you an option. Okay, so let's have some exercise. Right. Okay, so let's read the question. Dylan invests $3,000 at 6% compound annually. Calculate the value of his investment after 4 years. Okay, so and you might try to do it now by yourself. Okay, you can pause the video. Okay, and try to do it now. Okay. Okay, let's continue. Okay, so if I write Tn equal T0 times R to power n, that means I'm using the exponential growth idea or the geometric sequence idea. But you can always replace that Tn to suit your compound interest context. So that Tn just means the amount at the end of nth year. Okay, T0 means principal. Okay, and R, that means growth rate, not 6%, 1 plus 6% to the power n. Okay, so we are going to find the amount at the end of fourth year, and the principal with 3,000, and that's 1.06 to the power 4, right? Okay, just get this done. Okay, so that would be the amount, right? Okay, so B, how many years it takes for his investment worth 12,000. Okay. Okay, so let's see if I use that again. Okay, so this time is if I'm using this again. Okay, so the amount becomes 12,000. Principal is 3,000, right? Okay. Okay, so let's see. You can always divide this number. Okay, that's 4. Okay, so it becomes a similar question like the one we've done before. You need to find a power n to make it 1.06 greater than 4, all right? And you need to find this number of n to achieve that effect. But we have to do trial and error. Okay, you can do it by using a calculator. Okay, you can just plug in numbers one by one, but just as we have said, we can do it another way. Okay, so let's do it again. Okay, oh, sorry. Let's define again, but this time we're going to define as 1.06 to the, okay, let's see, make sure, yeah, 1.06 to power n. Okay, so that's n in the calculator must be x. Okay, all right, so you define it and then you can see what happens. Okay, so let's say, remember that this time you need to have that's x to make the number greater than 4. Okay, so possibly that x has to be very big. So let's see, 20. Okay, so you see when x is equal to 20 is still much less than 4. Okay, so let's make it bigger. Yeah, so let's, how about 30? Okay, now you see when it's 30 is bigger than 4, so let's try something between 20 and 30. So okay, so it's a bit greater, a little bit greater than 4. Okay, is 25 the answer? You still need to check whether 24 is also greater than 4, because we need the least number to make that happen, right? So let's try 24. Okay, you see that 24 still greater than 4 and is much closer than when you use 25, right? So let's see 23. Okay, so you see 23 is less than 4, so 23 is not qualified. 24 would be the least number. Okay, so the answer would be 24. Okay. Okay, so the least number is 24. Okay, therefore it takes at least 24 years. Okay, alright, so that's the question for this one. Okay, let's do another one. Okay, let's read the question first. Yeah, you might spend some time to read the question. Okay, and we can pause the video for a while. Okay, so if you have tried, you can check the answer now. Okay, calculate the amount for plan A at the end of investment. Okay, so there are two plans. The first plan is simple interest of 10%, okay, for 10 years. Okay, the second one is 9% compound annually for 10 years. Okay, both are for 10 years. And when you compare the interest rates, one's 10%, the other 9%. So possibly, by inspection, you might think plan A would be a better option. So how about your answer? Okay, so actually the answer would be quite surprising, okay, for some of you. Right, so let's see how could we do simple interest. Still remember that for simple interest, the amount at the end of each year follows an arithmetic sequence. Okay, so let's do it this way now. Okay, so the compound amounts of plan A at the end of investment. Okay, so for plan A is an arithmetic sequence. Remember that for an arithmetic sequence, for calculate the money, we start from T0, right? Okay, we use this form, but you need to interpret the AS into arithmetic sequence, into the simple interest one. So that's just AN. How about the T0 would be the principal, right? And N still N. How about D? D will be our interest, and interest is P times interest rate. Okay, right? Okay, so are we going to find after 10 years? Okay, so the principal is $5,000. 10 times $5,000 times 10%. All right. Okay, so after calculation, okay, $10,000 is doubled, right? Okay, so that's A. So let's see what happened to B. B is a compound interest, okay? So this time we are going to use compound interest formula. Okay, we are going to use this formula. Okay, Tn here means An, T0 means the principal, and R means 1 plus, that's R% per n. Okay, and we're going to find the amount at the end of 10th year. So 1 plus 9% this time, and that's 10 years. Right. Okay, so the amount will be, okay, I corrected to 2 decimal places. Okay, so when you compare, of course, plan B will give you more return. Okay, so how could we calculate the difference in interest earned? Okay, so of course we know that the principal are the same, so the difference between two amounts would be the difference in the interest earned, right? Okay, difference interest. Using this figure minus this figure. Okay, so that will be the difference between two investments. Okay, so you see the power of compound interest in this question. Even though you are you pay the interest rate per year is less than that for the simple interest, but over the time, at the end of 10th year, actually the amount accumulated will be higher because each year the principal is actually increasing. Okay, for compound interest investment, but for simple interest investment, the principal is always 5,000. So that's why that makes huge difference. Okay. All right. So that's all about compound interest. Okay. So remember, compound interest is what we call a type of exponential growth. So exponential growth means the quantities increase at a constant percentage for each fixed period of time. So how about if that quantity is not increasing but decreasing? Then we call them exponential decay. So what's an exponential decay? Exponential decay, just like exponential growth, but with a ratio less than 1. Okay. So exponential decay means the quantity is decreased at a constant rate. Okay. Okay. So for example, okay, just for example, okay, if number of students in a school is decreased 10% each year. Okay, then the decay factor. So previously we have a growth factor, now we have a decay factor. It's 1 minus 10%, so it's 90%, or 0.9. Okay, so if R is less than 1, so when you multiply that decay factor to the number becomes less and less, doesn't it? Okay, so how can we represent that using GS? It's just like a, so everything will be the same as the as what happens in exponential growth. Okay, so you can still represent the thing like Tn T0 R to power n. Okay, and that's Tn just means the amount at the end of nth year. Okay, the T0 just the initial amount. Okay, and that's R will be the decay factor. Okay, so decay factor is always equals 1 minus, not plus. Okay, so that's R%. The big R is what we call decay percentage. Okay, so we are going to use the same formula again. Okay, alright. Okay, so let's do one example. The population in city decreased by 5% each year. Okay, so when you see decreased, that means it's exponential decay, right? By 5% each year. If the population at the beginning of 2020 is 1.2 million, determines population at the beginning of 2025. Okay, so because both are at the beginning of certain year, so number of years between 2020 and 2025 will be 5 years, right? Okay, so let's see how could we calculate that. Again, we are going to use the same formula again. So it just be Tn equal T0 R to power n. So Tn will be our this case 5 years. T0 will be our okay. Oh, sorry, 1.2 million. Okay, sorry, 1.2 million. Okay, R will be decay factor. Remember, decay factor must be less than 1, so it must be 1 minus 5%. If that's growth factor, it becomes 1 plus 5%, right? Okay, to the power n. Okay. Okay, so it becomes 0.2929. Correct to easily configure million. Okay, so that will be the answer. Okay, so for the application of geometric sequence, you might see question like exponential growth, you might see compound interest, but compound interest is essentially just like an exponential growth. Okay, and you also you might also see exponential decay. In this case, just like exponential growth, but the factor, the common ratio become less than 1. Okay, and how could you get that common ratio? You use 1 take away the decay percentage. All right. Okay, so that would be the case. Okay, so in your notes, oh sorry, I need to Okay, so in the notes you see 14C, so you can do the 14C. There are 6 questions. You can try to do them as homework. Okay, so if you have any questions, please leave a message in the collaboration area. Okay, and see you next time. Bye.